So now let us discuss the various breakdown mechanisms in liquid dielectrics. Now, since we have kept on saying that dielectrics are chosen not only for their electrical functions or dielectric functions, dielectric properties, but also because of their non-electrical properties, where do we choose liquids for insulation? Where we need to fill up the available volume, so we need to fill up voids. Suppose you have solid insulation and you have a conductor and there are voids between the conductor and the solid insulation. You might use gases, you might use liquids to fill up the space between these whatever voids are there, to fill up the space between solids. Apart from that, liquids are often used where we need cooling properties, or sometimes they're also need where we need lubrication so that the liquid can kind of keep the surface lubricated. It is also used in arc extinction. Some liquids have arc quenching properties, and if you expect, for example, in circuit breakers where you expect arcs to happen, you need a medium which can quickly cause that arc to be extinguished. So insulating liquids are abundantly used in transformers, in power cables, circuit breakers, switches, etc., where apart from their insulating function, they perform the function of cooling, arc extinction, lubrication, filling up the void in solid insulation, etc. The most common and the cheapest liquid insulation that is used in practice is the mineral oil. Insulating oils can be both organic or inorganic in nature. Examples of organic insulating oils are mineral oil. Then there are synthetic oils like silicon oil, castor oil, etc. Nowadays we have vegetable oil which is being researched to see if they are a better bio-friendly option, a replacement for synthetic oils. You may have inorganic liquids like inorganic liquid dielectrics like highly purified water and its aqueous solution, and this kind is very often used for pulsed power technology. Then there are some recently introduced oils also like HDH, high temperature hydrocarbon, tetrachloroethylene, and polyether. So there are various types of insulating liquids which are available. Now, when you choose a particular liquid for use in a particular application, apart from its insulating properties, apart from its dielectric properties, there are two important things that need to be looked into. These are its heat transfer characteristics and its chemical stability, especially under electric stress. Because most of the time liquid is used when we need a cooling effect, so that means there is the possibility of some kind of temperature rise, at least local temperature rise. For example, to give you the example of a transformer. In a transformer, if there is a turn-to-turn failure or short circuit, there would be a high current flowing in a very small region, and the oil around that region can get very heated. And if a hotspot formation takes place in a particular region of the transformer oil, this can ultimately lead to catastrophic failure. So we would like the transformer to have sufficient heat transfer characteristic so that it can prevent hotspot formation. Essentially what we want is that there should not be any temperature buildup or heat buildup in one part of the material, in one part of the medium. Because once you have temperature rise, liquids also lose their viscosity. They become more viscous, which means the flow, the circulation of the liquids from the hotter regions to the liquid hotter region to the colder regions, cooler regions will be affected, and then their heat transfer characteristics will also be affected. So we need materials, we need liquids which have good heat transfer characteristics. The other important property that we need to look at is the chemical stability under electric stress. We are going to apply very high fills, and often enough there are materials, liquids, which are not chemically stable under electric stress. Chemical reactions can occur under high fills, and when chemical reactions occur, your original material breaks up into several byproducts. These byproducts may not be beneficial to the system to start with. They may not have good dielectric properties. They in fact may have unwelcome properties, like for example, there might be byproducts which are corrosive in nature, which are not capable of heat transfer, which undergo a lot of dielectric losses. So if you start with a particular material because you think it's a good dielectric medium, you do not want it to undergo chemical reaction and change into something which is not a good dielectric property. So apart from its dielectric properties, while choosing a liquid, we have to be careful about its heat transfer characteristics and its chemical stability. Now, having said that, what are the various processes by which breakdown can happen in liquids? We have to understand that there is still no comprehensive and one self-consistent theory which which can explain the physical mechanism of liquid breakdown. However, we have several theories which can very satisfactorily explain breakdowns under certain conditions. And some of these theories are nothing but extensions of the theories that are applicable to gases. For example, the avalanche model. However, if you're going to apply the avalanche model, of course, means that you're talking about multiplication of electrons. So availability of free electrons and multiplication of electrons such that they create an avalanche which can ultimately lead to complete breakdown. That kind of process, if that kind of process is going to be responsible for breakdown, then that is only possible when we have liquids of extreme purity. Only in extremely pure liquids, electronic avalanche can cause breakdown. Otherwise, there will be some other mechanism which is likely to cause breakdown. I'll come to that later. Now, liquids are most often not in very pure form, and as with the passage of time, most commercially exploited liquid insulation with the passage of time become highly impure, acquire a lot of impurities. These impurities can be foreign solid particles, so solid impurities, either metallic or fibrous, which can ingress into the medium from various parts, from the transfer tank, from the conductors, from small breakages, from dust. So there might be various sources from which foreign particles can invades into the liquid medium. The other thing that can happen is when you have liquids and you have temperature fluctuations, bubbles may be formed, or there may be byproduct formation due to chemical reaction, and as a result, gases may be trapped in bubbles inside the liquid. And the presence of such foreign particles, either solid or gaseous in nature, can have a profound effect on the breakdown strength of the material. So when you're talking about electronic processes, you're talking about material breakdown strength, which is dependent only on the material. But in reality, it is not the material which decides. Of course, to a certain extent, what material you choose decides its breakdown strength, but in liquids, the state of the liquids, the state of purity, how many foreign particles are there, what is the nature of the foreign particles that are present in the liquid, the presence of these foreign particles are the ones which ultimately decide its breakdown strength. And therefore, these are the processes that we need to understand. If we just quickly look at the electronic breakdown, when you see that you perform breakdown measurements on liquids, and you see that these breakdown measurements show little temperature dependence. That means you are conducting experiments at various temperatures, and at all these temperatures, you are getting the same value of the breakdown strength. It would indicate that there is a high possibility that the breakdown mechanism in this case is electronic in nature. Not only is it electronic in nature, it is also a process by which the cathode injects electrons into the gaseous medium, which is temperature independent. So it cannot be thermionic emission, it is likely to be field emission. So that means if you have breakdown measurements showing that the breakdown strength of the material is independent of temperature and only dependent on the material, the breakdown mechanism in that case is likely to be electronic in nature. And not only that, the electrons are available due to field emission at the cathode. Once the electrons are injected, they are accelerated by the fields, and hopefully they have enough long mean free paths such that they gain sufficient energy to cause collisions to cause ionization when they collide with other particles. And this must happen so often that avalanches can be initiated. So gain in energy of an electron over its mean free path must be equal to that required for ionization of a molecule. So small e capital E into lambda must be equal to CH nu, which is the amount of ionization electrons which is required, and ionization energy that is required. The electronic theory actually can satisfactorily predict the relative magnitude of breakdown strengths of liquid. So if you think in terms of electronic breakdown, it can explain why certain liquids have lower breakdown strength and certain other liquids have a higher breakdown strength. It makes complete sense. But it does not explain the time that is required. If it is electronic breakdown that you are expecting, you expect a certain formative time lag. The electronic breakdown mechanism predicts a certain formative time lag between the application of the field and the time at which breakdown happens. However, in reality, you will find that breakdown takes much longer time. So this is kind of indicative that in practical scenarios, the electronic breakdown can probably initiate the breakdown mechanism, but it is unlikely to be solely responsible, or maybe it is not at all responsible for the breakdown actually happening in a practical liquid, because we find that in such scenarios, in the practical scenario, the breakdown takes much longer time. Electronic breakdown predicts a shorter time, but in reality, liquid breakdown takes a longer time. So electronic breakdown may have a role to play, but it cannot have a complete role to play, and there must be other processes which are involved. And those processes are dependent on the nature of impurities in the liquids. So we need to understand that how does suspended particles or trapped bubbles affect the breakdown mechanism in liquids?